Hi, I'm Jack Deslip from Berkeley Lab. I'm really excited that my colleagues and I have the chance to share our recent advances in HPC-guided materials design with you here today. We're a team of 6 researchers and engineers from Berkeley Lab, UC Berkeley, and Stanford. Come on, some might say that we should get an award just for bringing those last 2 schools together. Today you're going to hear from 3 of our team members. First, to describe the background of the material science grand challenges that we're tackling. Secondly, to describe how we are exploiting multiple levels of parallelism in HPC leadership class systems. And finally, to describe how we fine-tune performance on the Oak Ridge Summit system with NVIDIA V100 accelerators. To get us started off here is my colleague, Felipe Jornada. Felipe, take it away.
Thanks, Jack. My name is Felipe Jornada. I'm an assistant professor in the Department of Material Science and Engineering at Stanford University. Now, to fully appreciate the topic that we'll be discussing today, it is important to think about our history, the history of humankind, which can be divided into materials that make each period. From the Stone Age to the Steel Age to the current Silicon Age, materials often define our daily lives and our available technologies. Silicon, in fact, started a revolution. Unlike, say, steel or plastics, we're less interested in how silicon behaves structurally, but rather when it's perturbed or excited. For instance, controlling and understanding electronic excitation in silicon has allowed us to design transistors that have shaped our current information era. And similarly, engineering optical response in silicon has allowed us to generate efficient and inexpensive solar panels for renewable energy sourcing. The future will likely accelerate this trend, where advances in nanoscience will allow us to design novel materials with atomistic precision and which react differently to external stimuli. 2 examples of transformative applications involve next-generation cheap, reliable, and ubiquitous photovoltaics. And for these applications, we need to understand how electrons and holes can be excited in these materials, how they relax, and how they can be eventually separated to drive electrical current. Now, an even more transformative system is that for quantum information approaches. It turns out that defects in materials are promising systems for qubits, which are the building blocks of future quantum computers. The problem, unfortunately, is that understanding excited state properties of materials is orders of magnitude more complicated than understanding the ground state properties, which are the ones that dictate structural properties. The reason is that in order to understand excited states, we need to account for the complicated quantum mechanical many-body interaction between all the electrons. Now, a common approach to do so is with the so-called first principles GW approximation, which gives you accurate electronic excitations in materials. But while accurate for excitations, this method is much more expensive than methods that are used for ground state structural properties, such as density functional theory. For instance, the GW approach scales cubically, or to the 4th power typically, with a number of atoms, while density functional theory scales cubically and force field approaches typically linearly with the problem side. To give you an idea of what this means, up to roughly a decade ago, we could only study systems with a few hundred atoms. But the work that we're going to be presenting today breaks the record of large-scale calculations of excited states with over 10,000 valence electrons in the simulation cell and utilizing over 60 total exaflops for the calculation. The work we'll be presenting today shows how we can utilize a combination of code optimization and massively parallel computer calculations to predict and design transformative and much more complicated systems for those applications. We showcase here how we can study a prototypical system, that of defects in silicon and silicon carbide, which are prototypes for defects for qubits, which can be used for next-generation quantum computers. So in a sense, we're using here high-performance calculations to design new materials for future quantum computers. The summary of our work here is that we performed the largest ever high-fidelity GW calculations with over 10,000 valence electrons, and we achieve over 100 petaflops per second of performance with a time to solution of roughly 10 minutes. And with that said, I'd like to pass the spotlight to Mauro.
Thanks, Felipe. I'm Mauro Delben from the Computational Research Division at Berkeley Lab. And in this segment, I'll summarize the portability strategy for multi-GPU, multi-node implementation in BerkeleyGW. BerkeleyGW is a massively parallel software package employed to study the excited states properties of electrons in materials, employing the GW method and beyond. In GW, the dynamical properties of the electrons are obtained as the solution of the Dyson equation given here. And in the Dyson equation, the complicated quantum mechanical interaction among the electrons are described by an effective potential known as the self-energy and symbolized with sigma. The self-energy is a complex, non-Hermitian, non-local frequency-dependent operator, and its evaluation represents the computationally intense part of any GW workflow. The solution of the Dyson equation in BerkeleyGW faces two major bottlenecks. The first one is the evaluation of the inverse dielectric function, or epsilon inverse, and the second is the evaluation of a set of self-energy matrix elements from the inverse dielectric function. And in BerkeleyGW, these two bottlenecks are implemented in two standalone modules, namely epsilon and sigma. So in epsilon, there are three major computational kernels: the matrix elements, MTXL, based on fast Fourier transformation; the chi0 kernel, computing the polarizability matrix, based on complex matrix-matrix multiplication, or ZGEM; and a final matrix inversion to compute the inverse dielectric function. For large-scale application, the chi0 kernel is by far the most computationally intense part of the calculation, and is usually implemented as a large distributed matrix-matrix multiplication over fat and short matrices. In sigma, the core computation is the evaluation of a set between 100 and 1,000 matrix elements of the self-energy operator, depending on the system size. Within the generalized Plasmon pole model, the GPP model, the working equation is given here and is implemented in the so-called GPP kernel. Eventually, for each of these self-energy matrix elements, the GPP kernel is carrying out a big data reduction across different matrices with a complex matrix vector interdependence. In the following, I'm going to give you a little bit more details about the GPU acceleration and parallel implementation of the chi0 kernel and the GPP kernel. So for chi0, which is implemented this large distributed matrix-matrix multiplication, in a parallel run, the data layout is given here. And the matrix is distributed over MPI task by distributing the columns. And to give you an idea, for a large-scale application, the number of the rows can be easily of the order of hundreds of thousands, and the number of columns can easily exceed hundreds of millions. Now, the resulting matrix chi0 after the matrix multiplication is instead distributed using a 2D block cyclic distribution, so that in the next step, which is a matrix inversion, we can use an external library such as the scale-up library. At the GPU level, the matrix multiplication is performed by using the ZGEM implementation of the cuBLAST library. And three major strategies have been implemented in order to achieve the optimal performance on thousands of GPUs. The first one is what we call offload of data preparation. Since the data layout between the starting and ending matrix is different, some sort of data preparation needs to be performed before actually executing the ZGEM. And you can do this operation, offloading the matrix elements to the GPU in order to accelerate this preparation step. On the other hand, due to the limited memory on the GPU, this can be potentially a memory bottleneck for large-scale application. And to alleviate this problem, we have implemented the second strategy, which is a batching mechanism, which avoids hitting the memory limit on the GPU by loading the column of them depending on the maximum memory on the GPU. This implies that for each of these batches, you have to repeat the communication scheme, which is the final techniques we have implemented. We have moved in the direction of a non-blocking cyclic point-to-point communication scheme, which eventually offered the possibility to overlap the MPI communication on the host with the ZGEM execution on the GPU. So for sigma, we need to evaluate a set of self-energy matrix elements. And in sigma, we actually employ a two-level parallelization strategy. So the total number of MPI tasks is divided into pool of process, so what we call the interpool parallelization. And each of these pools is actually working on independently on a subset of self-energy matrix elements, or what we call the interpool parallelization. So the data layout of the interpool parallelization is shown here. And similarly to the chi0 kernel, by using a non-blocking cyclic communication scheme, we are effectively able to overlap the MPI communication on the host with execution of the GPP kernel on the GPU. The computationally intense part in sigma is entirely executed on the GPU. The working equation for the GPP kernel is shown here. And these eventually represent this complex multi-GPU, multi-node data reduction. The detailed description of the various optimization steps we have implemented for this GPP kernel will be discussed later by Sherlyn, which will describe this in great detail. So after this short introduction, I'll move to the performance result for epsilon and sigma, which will be summarized in terms of acceleration of the GPU version compared to the CPU version, weak scaling, and strong scaling. So the performance were measured on 3 HPC systems. Of course, Summit at OSCF comprised of 4,600 nodes, each with 2 IBM Power 9 CPU and 6 V100 GPUs. The Cori GPU cluster is a small cluster at NERSC with 18 nodes, each having 2 Intel Skylake CPU and 8 NVIDIA V100 GPUs. And some of the CPU-only benchmark results have been measured on the Cori Haswell partition at NERSC. The benchmark system employed for the performance measure are based on real-type application, in particular point defect in semiconductors such as silicon and silicon carbide, which actually have important application as prototype for solid-state qubits. The system size range from moderate, few hundred atoms, up to extremely large. And here is the example of the largest system, which is comprised of almost 3,000 atoms and roughly 11,000 electrons. I want to remark that this calculation represents truly large-scale application. The completion requires order of hundreds of terabytes of virtual memory, and the total number of flops is of the order of tens of exaflops for completion. We start here showing the speed up observed when using the GPU implementation instead of the CPU-only implementation. And for Epsilon, we show the result on 2 Cori GPU nodes for a medium-sized application, only 214 atoms. And we show here that the 2 accelerated kernels, that is MTXL, but in particular Chi0, are both accelerated by 20x or more. And overall, once we consider the overall time to solution, the speed up is 18.6x. For sigma, we compare instead the time to solution by running on Summit and the Cori Haswell partition at NERSC over a wide range of number of nodes. And once we do a one-to-one node comparison, we achieve an 86x speed up across the 2 architectures. Next, we report the weak scaling for both epsilon and sigma as measured on Summit. In both cases, we are focusing the analysis on the quartic scaling bottlenecks of the 2 modules, that is Chi0 kernel for epsilon and the GPP kernel for sigma. Overall good weak scaling is observed within 5% in both cases, and this is the result mainly of the batching mechanism for memory handling in epsilon and the efficient 2-level parallelization we have in sigma. Strong scaling for epsilon is shown here as measured on Summit for the 2 largest systems, that is the silicon carbide with 998 atoms and the silicon system with 2,742 atoms. Good strong scaling is obtained up to 1,000 of GPUs, in particular for the Chi0 kernel, that is once we exclude the I/O and the inversion step, which is still performed on the host. Eventually, for the silicon carbide with 998 atoms, the drift of linearity we see from the 9600 run and the 14,400 GPU is the result of the reduced flop on the GPU that result in a loss of effectiveness between the overlap of the communication on the host and the computation on the GPU, and also due to load imbalances issues for the larger node count. Sigma instead scales much better than epsilon thanks to the 2-level parallelization we have implemented, and excellent strong scaling is demonstrated up to the entire Summit, so over 27,000 GPUs. Here we report the result for the 2 largest systems, the silicon carbide and silicon, by including the I/O, so total time to solution, and excluding I/O. So it is clear that for the largest run, beyond 20,000 GPUs, the I/O starts to be relevant, so the time for the input-output starts to be non-negligible for the total time to solution. So in order to improve I/O performance, we can actually exploit the high-performance node local solid-state memory on Summit. In order to do so, we pre-process the data into a distributed form prior to the full scale execution. This can be performed at no cost, and this data distributed in a distributed form can be reused for multiple runs. Then, before running Sigma, the data in a distributed form are pre-staged on the node local SSD, and once we run the full application, each of the NPI tasks is now able to read directly the distributed data from the high-performance node local SSD. So we finally show here the best performance in terms of scaling for Sigma. And we show the improvement compared to the previous run. In particular, at full scale, by using the pre-stage on SSD, the I/O time is improved by over 10x, reducing from 266 seconds to 23 seconds. Here, I just want to note that the newer result includes some further optimization of the GPP kernel, which have further improved the time to solution specifically for this kernel. This is actually the topic of the next section, so I'm going to pass the presentation to Charlene, which will be focusing on the various levels of optimization we have implemented in order to achieve the best performance for the GPP kernel.
Hi, I'm Charlene Yang from NERSC, Lawrence Berkeley National Lab. In this segment, I'm going to take us for a deeper dive, and we'll talk about some of the optimizations we did for Sigma. Sigma, the most time-consuming kernel is the GPP kernel, the general Plasmon pole kernel. As you can see from this profile, this kernel takes up over 90% of the runtime. And for the problem we're calculating, there are thousands of these kernels on each GPU. Given this importance of this kernel, we want to take a deeper look into its performance bottlenecks and possible optimizations. For the most part, this kernel contains 4 nested loops, and these loops iterate over the conduction and valence bands, the G prime vectors, G vectors, and frequencies. These loops vary in length from a few iterations to hundreds of thousands of iterations. But overall, they provide an abundance of parallelism, perfect for GPU computing. This kernel performs a tensor contraction-like operation, which means that we could be bandwidth bound. Because we're sifting through a lot of data, but only perform low-rank reductions on them. This reduction of trillions of numbers in each kernel requires some storage of the partial sums, and we have been using the shared memory for this. On average, we use 32 to 48 kilobytes of shared memory per thread block, and this has been one of the factors that limit our occupancy. The other factor is our register usage. Because we use double precision complex numbers, and our kernel is very long, we use 80 to 90 registers per thread, and this has been further limiting our ability to hide the latency. On top of these challenges, we also have to deal with the complicated memory access patterns because we have quite a few very large multidimensional arrays to read in. We also have a few long latency operations like divisions and square roots, and that doesn't make our life easy either. To overcome these challenges, we have implemented these 8 optimization steps. And through these optimizations, we have achieved a 2.8 times speedup in runtime. Without going into the details, I'm going to touch on a few of them. First is the replacement of these divisions and square roots in order to reduce our execution latency. Secondly, we have reordered some of the loops in order to gain arithmetic intensity. Thirdly, to reduce the memory latency, we have applied these 3 steps. Without further ado, let's jump into it. Like I mentioned earlier, we want to reduce the execution latency because it's causing a lot of warp stalls. On this inside compute profile, you can see that there's a very high percentage of warp weights, contributing to 52% of the warp stalls. According to this kernel profiling guide, warp weights are caused by long execution dependencies, and divisions and square roots are some of the obvious culprits. So we have replaced the complex number divisions with reciprocals and square root calculations with power of 2 calculations. The second replacement is possible because the results are only used for condition evaluations, for example, in the if-else statements. After this optimization, our warp weights have dramatically dropped, as seen on this new inside compute profile. Here, the long scoreboards have become more pronounced, but let's worry about them a bit later. On the roofline chart, we see slight improvement on our throughput, even though our runtime has improved by 40%. This mismatch in improvement is because during this process, our total number of floating point operations has also changed. and roofline tracks throughput rather than time. What's most notable about this roofline chart is that our kernel has become very bandwidth bound. And this is seen by comparing this green square symbol and the green HBM ceiling. This closeness means that we're limited by how fast we can move data in and out of HBM, not by any other caches, not by the compute. This ceiling defines our maximum attainable peak, so if we stay at this arithmetic intensity, we can't move further up. However, if we move to the right, we may gain more headroom and therefore more potential for performance. To do this, we have rearranged our loops a little bit. The original implementation follows the natural expression of the physical equations, but now we have moved some of the band loop iterations inside. This way, the IG and the IGP loops can still provide the parallelisms we need for GPU computing, but the band loop can also provide some cache locality for some of the arrays related to the band index. A few considerations have gone into this step. First, we want to make sure that there's still sufficient parallelism in order to efficiently utilize the GPUs. Secondly, the loop that we want to move in has to be carefully chosen because we don't want to bring too much disruption to the memory access patterns. And we already have quite a few multidimensional arrays in this kernel. Thirdly, the band loop needs to be small enough so that it doesn't blow the lower level caches, for example, the L2 cache. After this optimization, our runtime has improved by 24%, and our kernel has moved to the right on the roofline. With the increased L2 and HBM arithmetic intensities, we're now well into the compute band region. In the next few steps, we'll try to make better use of the compute resources, and maybe we can push the performance further up. Here, I would like to point out that the compute peak we use is 6.7 teraflops, because as validated by on-site compute, our GPUs are operating at the canonical frequency, which is 1312 megahertz. You may be thinking about the 7.8, but that is based on the turbo frequency. It would be prudent to check the frequency and the exact compute ceilings so that you don't overestimate the peak or underestimate your performance. Utilizing the compute resources includes utilizing more GPU threads. At the end of the day, GPU computing is all about latency hiding. So it's always a good practice to keep an eye on the kernel launch parameters so that we have enough active warps to choose from. Experimenting with the max reg count of the NVIDIA compilers could also be rewarding. In our case, by tweaking this flag, we have gained another thread block. Even though more register spills have occurred, the higher occupancy has proven to be very beneficial, as can be seen on this speed of light chart on on-site compute. Squeezing more threads out of the compilers has helped, but on profiling, we have noticed that there's still a lot of long scoreboard counts, especially on this line. In on-site compute terms, long scoreboard means that there could be inefficient accesses to the global memory. In the next two steps, we'll see if we can try and address this. So we have applied some cache blocking to the IG and IGP loops, and also moved a couple more arrays into the shared memory. This has helped reduce the memory latency from 85% in the fifth version to now 63%. Some extra care has to go into these two steps. For example, the block size in step 7 needs to be carefully tuned. Also, because the shared memory is a very scarce resource, we want to only put small arrays that are frequently used into the shared memory. With these optimizations, our performance has landed at 3.9 teraflops. And if we compare to the peak, 6.7 teraflops, we are at 58 hardware utilization. This 6.7 is for 100% FMA ratios, but you probably know that almost no applications can reach 100% FMA ratio. So it's almost meaningless to compare to that peak. In order to better understand our performance, we have measured the actual FMA ratio in our code using on-site compute. And this has come out at 51%. Now, based on this little equation here, we can derive our more customized peak to be 5.1 teraflops. And compared to this peak, we're at 76%. This is very impressive given all the challenges we have, including the complex number arithmetics, the high register count, high shared memory usage, low occupancy, and long latency instructions. So to quickly summarize, we have achieved a 3.9 teraflops performance on the kernel level. And through these optimizations, we have improved our runtime by 2.8 times. On an application level, we have run on the full system of Summit, and we have achieved a 105 petaflops performance. This is in double precision, and it's 52% of the theoretical peak and 71% of the LIMPAC peak of Summit. So many of the challenges, many of the computational characteristics I've talked about here are very common to other HPC applications. So hopefully some of our lessons learned can be useful to you as well.
To summarize what we've presented today, I want to emphasize 3 exciting plots and 3 really exciting numbers. Let's start with the plots. The first plot shows near perfect strong scaling to full Summit system, including I/O. The second plot shows excellent weak scaling as we double the system size. And finally, the third plot shows an order of magnitude energy to solution improvement as we move from the Cori Intel Xeon system to the Summit accelerated system. You know, I might have had to hide my face around NERSC after showing these numbers, but thankfully we'll be deploying our own GPU accelerated system with the new NVIDIA A100 accelerators in just a few months. Now we'll finish with the 3 numbers. First, over 10,000 electrons. That represents the largest calculation of excited state electronic structure ever done at this fidelity. Second, over 105 petaflops of double precision performance. The method, the algorithm, and the software are well positioned to make use of current leadership class systems, and we're achieving up to 72% of system LIMPAC peak on Summit. And finally, time to solution of only 10 minutes. This allows us to evaluate many configurations with near real-time analysis. And what's really exciting about the combination of these numbers is that together they usher in the practical use of the high-fidelity GW method to the study of realistic complex materials, materials with defects, with interfaces, with large geometries that drive real device design and quantum information, energy generation, and storage, and next-gen electronics. I'm super excited for what the community is going to do with this capability. We have a number of important people and institutions to acknowledge: the DOE Basic Energy Science Computational Material Center, C2 CEPM, support from the OLCF through Insight, and help from Catalyst David Rogers, each of our own institutions, and support from NVIDIA, particularly Brent Lelbeck for expert advice. So here are our funding acknowledgments in all their full verbose glory. It's been a real pleasure sharing our excitement with you today. Thank you for your time and consideration.